Okay, let's get started, please. So I'd like to welcome everybody to this final workshop of the Resurgence program. I'm not the director. The director is stuck in traffic, so she will hopefully be able to talk to us this afternoon. So we've overcome many things to get to this point, so we're very happy to be here, and we'll be starting off with a talk by Ricardo Schiappa on resurgence of negativity. And I remind you there's plenty of time for questions at the end of the talk, so please ask some. So, Ricardo.
Thank you. Thank you, Gerald, for the invitation. And thanks to the Newton Institute for having hosted us here for the past 3 months. And I will be, in fact, talking about work that we've done here during that time. And to be slightly more precise, I mean, with this title, I could talk about pretty much anything that goes on in the world today. But I'm going to be talking about something that happened in string theory, deep brain negativity. All right, as I said, this is work that we've done over the past 3 months with my students, Max and Noam. They're here in the audience, and feel free to talk to them about this stuff if you're interested, which will appear, I don't know, maybe sometime later in the month. Of course, this doesn't come out of the blue, and it builds up in earlier work we did, also with Max and Marcos Marinho, that came out in October, and earlier in the spring with my students. All right, so Gerald asked me to do sort of a colloquium-style talk. So it will be quite cartoonish, the first part, so that everybody's on board because of the diversity of the audience. So let's start with, I mean, there's also experts in the audience. For those, I apologize for the first, I don't know, 20 slides. But let's try to make sure that everybody's on board with what's going on. All right, so the first thing to just mention is gauge theory. So, you know, forces in nature are described by gauge theory, and particularly the nuclear force is described by a gauge theory, which is strongly coupled. So we don't have a natural parameter to do perturbation theory, so it's kind of hard. So already a long time ago, almost 50 years ago, next year I think, Tuft told us that one way to try to go around this is to tackle the large n limit. So we consider SUN gauge theory when n is very large, in a particular limit where the coupling, which is G Yang-Mills times n, is held fixed. Lambda is the Tuft parameter. If you do this, then you find a natural perturbation parameter, which is 1 over n, and the free energy, the logarithm of the partition function, has a very nice expansion, which is asymptotic. So that's something that should resonate with this audience. And if you read the fine print of a Tuft paper, it says, let me quote, the 1 over n expansion may be a reasonable perturbation expansion in spite of the fact that n is not very big. So n is 3, but so it's a funny quote from his paper. So what happens is that Feynman diagrams actually simplify. So these Feynman diagrams are these sort of double lines, and they're organized in such a way that you can draw them on top of a sphere at large n, and then there's subleading corrections that you can draw on top of a torus, a bitorus, and so on. And this perturbative expansion is asymptotic in 1 over n squared. And the perturbative coefficients, those guys over there, they grow 2g factorially fast. Of course, they also have a lambda dependence, but that's exponential growth. It's subleading. It's not the leading growth, which is factorial. So one question that we could have is, how do we deal with this asymptotic series? What can we do with it? Around the same time, a quite actually similar problem appeared, which was, this was early 70s. People started talking about string theory. And string theory was defined back in the day perturbatively. I mean, even today, generically, there's no non-perturbative definition. In some backgrounds, there is. And the way it's done, it's quite similar to what we just had before. We have a sum over surfaces of different genera, now weighted by G string. That's a string coupling. You can think about it as H bar. And if I compute the free energy, the logarithm of the partition function, something quite similar also occurs. I have some free energies at genus G. They depend on T. T is, you can think about it as the size of the space-time where strings are propagated. And this, again, is an asymptotic series, now in GS squared instead of 1 over n squared. And the coefficients grow as 2g factorially fast. They also have t dependence. That's subleading. It's exponential growth. So the first thing you notice is, of course, that they're very similar. Here I have a gs squared, 2g factorial growth. And here I have 1 over n squared, 2g factorial growth. So you could ask, might there be any relation? I mean, they look the same. Could they also be physically the same? And this, of course, is also a very well-known story. For 30 years, people were thinking that that could be the case. And it turned out that it was actually the case, as was shown by Maldacena roughly 25 years ago. So there's a gauge theory. It's not exactly the same that I was telling before, but it's just to convey the idea. Now it's supersymmetric as 4 supersymmetries in 4 dimensions. That's Lagrangian. And it's actually the same as string theory and ADS. Here's a cartoon from Wikipedia of what ADS is. So if you don't know what that spacetime is, just think about it as sort of a gravitational well. Like in quantum mechanics, you would have a square well. This is an infinite square well in gravitation. And these things are the same. So it is very natural to ask, all right, we have asymptotic series that appear in string theory. You have asymptotic series that appear in gauge theory. They're the same. They have these properties. They're expanded in powers of the coupling square. They grow 2g factorially fast. What are the non-perturbative corrections that these things can have? The naive expectation is that the gauge theory would have non-perturbative corrections of the type e to the minus n squared and string theory of the type e to the minus 1 over gs squared. This is not what happens. That's the first surprise that happened already back in the 90s, is that the naive expectation is not correct. And what really happens is that in gauge theory, and from now on, for gauge theory, I'll mostly be focusing on gauge theories in 0 dimensions. This is just matrix model. The leading non-perturbative corrections are much stronger. They're e to the minus n. And this was shown by François David back in the 90s. They're associated to eigenvalue tunneling. What do I mean? So here I have the spectral curve of my random matrix model, which is genus 0 with the pinch. So this has nothing to do with the previous surfaces. Of course, it's sort of target space geometry. And I have the cut where eigenvalues sit. And I can remove an eigenvalue from the cut and put it at a non-perturbative saddle. That's eigenvalue tunneling. It gives me a correction of the type e to the minus n. And that's the leading non-perturbative corrections. In string theory, the same sort of surprise happens. This was shown by Polchinski also in the 90s. There's actually, besides having closed strings, there's also open strings around in the theory. And they have to attach to specific objects known as d-branes. And it turns out that if you do the correct combinatorics of d-branes, and I'll get back to it in a few slides, then they give terms of the power e to the minus 1 over gs. So again, much stronger non-perturbative corrections than you would expect. So one thing you can ask is, where's the e to the minus n squared? And where's the e to the minus 1 over gs squared? I will have basically nothing to say about that. But it's a fair question. So, OK, fine. You say, great, that there's that peculiarity, that the leading non-perturbative corrections are much stronger than we would expect. But that's about it. Well, that's not about it. There's a second surprise that occurs when you start doing examples. And we've worked out many examples. The Polinville-1 equation, which is sort of probably cherished by many people in the audience, matrix models, multi-critical models, minimal strings. There's a plethora of models that you can try out. And what do you find? The structure of the trans series, of the non-perturbative structure of these string theories, or these gauge theories in 0 dimensions, like matrix models that you find, is of this type. So you have a perturbative series that's gs squared. That's sort of representing the perturbative series. Then you have terms of e to the minus 1 over gs, either d-branes, a single d-brane or a single eigenvalue tunneling. And there's a perturbative theory associated with it, 2 d-branes, and so on and so forth. But which would be the naive sorry, wrong slide. Did I already tell you what is the answer? Yes, way too many. So the naive thing would be to have this sort of horizontal line. But that's not all. If you only have that, you cannot describe the contents of your theory. You also need to have terms of the type e to the plus 1 over gs, plus 2 over gs. And then terms which are of plus 1 over gs, minus 1 over gs, which give order 1 but non-perturbative, also in gs squared. And you need to sort of populate this whole square. So there's more than just eigenvalue tunneling, and there's more than just d-branes. So what could these things be? So these are things that you can check not only analytically by constructing these trans-series solutions to these problems, but also there's a lot of numerical checks. And this slide is not supposed to be readable. It's really just to convey the idea that we've tested this extensively, And I mean, we pretty much have absolutely no doubt that those terms are there. So what might they be? This is the key feature of this trend series. The Borel plane is symmetric, plus minus. So whenever I have singularities on the positive side, this, by the way, this is an example. Let me tell you which one. I will come back to it later on. It doesn't matter which example it is. They're all basically have the same features. This is JT gravity, and we have about 60 guys in the perturbative, and we're plotting using a Borel-Padé approximation to the Borel singularities on the Borel plane of JT gravity. And those are the leading singularities, and these are the Borel-Padé poles, which are sort of telling you about the branch cuts. And the key feature that all these systems have is that they are symmetric. So the singularities on the Borel plane appear at plus and minus, which we call this resonance. All these examples have this feature, and the resonance is what tells you that you have the plus and the minus of all non-perturbative guys. All right, so this is not enough. So eigenvalue tunneling and on the gauge theory side, or matrix model side, and D-branes in the string theory side, they're, well, at least for 3 slides now, familiar non-perturbative corrections, but they're not the whole story. So what else are we missing? Well, we're missing 2 things. From the gauge theory, or the matrix model side, we're missing anti-eigenvalue tunnel. What does that mean? That means that in the standard calculations that you do in matrix models, you grab an eigenvalue from the cut, and you move it along the physical sheet. I mean, all these Riemann surfaces are basically, well, in the simplest cases, they're basically hyperlytic. And so you can just basically think of it as a double cover over the complex plane. And we usually move an eigenvalue to the cut. Now we can have to move an eigenvalue along the non-physical sheet to the non-perturbative saddle. And it turns out that if you look at how correlators behave in the matrix model, this is the same as moving an anti-eigenvalue on the physical sheet. It's a little bit like this story of the Dirac sea, that you remove one guy and you put it into the sea and it behaves like a hole on the physical sheet. The second thing, that what is the analog, so that gives it the plus n. The second thing that gives the plus 1 over GS are negative tension D-branes. This is really something which has basically almost nothing to say. It's just I grab my D-brane boundary state and I put the overall minus sign in front of it. You could say, well, that's terribly naive. I mean, that cannot give anything non-trivial. Well, as we'll see later, it actually gives extremely non-trivial content. These negative tension D-branes are not new. They've been studied in the literature previously. But if you go and read these papers, people are basically always saying, well, maybe they're there, not there. We're not really sure. They look a little bit odd. They have lots of weird features. In space-time, they create several time-like directions and so on. And certainly, they've never been addressed from the point of view of asymptotics. So what we're basically saying is that you cannot live without these guys. So resurgence requires that you have negative tension D-branes, the same way that resurgence requires that you have anti-eigenvalue tunnel. And so the structure of these systems generically is going to be trend series of this type. So I'll have perturbative sectors. I'll have multi-instanton and multi-resurgent instanton sectors, and everybody mixed together. And they will basically be in line along directions of the resonant kernel, because this is always plus minus, so there's a natural 45-degree resonant kernel direction. So the real nature of the large N expansion is of this type. So there's a spectral curve which gives you the standard, I don't know, via topological recursion, for example, gives you the standard 1 over n squared expansion. There's going to be eigenvalue tunneling that's going to give you e to the minus n corrections. There's going to be anti-eigenvalue tunneling that gives you e to the plus n corrections. Likely, there's also e to the minus n squared corrections. We don't know where they are. They're hidden, like really far away on the Borel plane. And whether they're resonant or not, I do not know at this stage. And string theory should be similar. So there's the GS squared expansion, the standard sum over genera. There's standard D-branes that give you e to the minus 1 over GS corrections. And there's going to be negative tension D-branes that gives you e to the plus 1 over GS corrections. There's also e to the minus 1 over GS squared correction. Certainly in the superstring, they're associated to the NS5 brane. We still haven't been able to see them in asymptotics. We don't know if they're resonant or not. On top of all of this, there's Stokes data. Stokes data will also be, come into the game with resonance. Here I'm showing Stokes data for polynomial 1, a system that should be familiar to everyone. It organizes into vectors, which are mainly on the third quadrant. And I will tell you about these vectors later. For now, just tell you that you just need to know a few numbers, and you pretty much know everybody. And there's this number, which is associated to eigenvalue tunneling, has been computed by François David in 92 or 93, I'm not sure. And so this is the one that you could say that it's associated to anti-eigenvalue tunnel. And it has another Mascheroni, so it's transcendental people. And this can be analytically computed from matrix integrals, if you think about this construction a la gauge theory, or they can be constructed from boundary conformal field theory, if you think about these negative tension D-branes. So you can compute all these numbers, and these numbers can then be checked very carefully against asymptotics and polynomial 1, or in other models. So we have many different systems, and all these things seem to be related to each other in the sense that I always have a counterpart. So if I talk about matrix models, I find eigenvalue, anti-eigenvalue tunneling. They have counterparts in minimal strings or string equations or topological strings as D-branes and negative tension D-branes. I can get Stokes data out of this. So there's lots of relations between these things. And to sort of convince you that this is the structure that we're finding in large N gauge theory and in string theory, I'm going to basically pretty much compute the same quantity in several different ways and show that you get exactly the same result. So in a recent talk on YouTube, Maldaceno giving advice to young students, he said, think globally but act locally. So let's not try to solve every problem at once. So we're going to follow exactly his advice and look at examples which are under analytic control. Matrix models, Liouville theory, minimal strings, JT gravity, topological strings, strings in ADS3, all these things we can sort of do calculations. So we're going to be far away from, ADS CFT n equals 4. I mean, that's very hard. I honestly don't know how to do calculation there. But I know how to do in this simpler example, so hopefully that will give you enough evidence. All right, so that was sort of the cartoonish part of the talk. Let me now give you the calculational part of this talk. So this was our office in the past 3 months, which we shared with other colleagues that are here in the audience. So the first thing I should say is apologize for all the noise that me and my students were doing, constantly trying to work these calculations out. But anyway. So the first thing we can try to compute is using string equations. So in many of these models, we have differential equations that allow us to do, easy calculations. So I'm just going to, give some flavor of the calculations. I will not be going through all the details, but hopefully it will be convincing. So when we're dealing with multi-critical models or minimal strings, they're described by differential equations. So the way we want to compute free energies, that's F over there. And we do that by using differential equations for U. That's the specific heat, which is fine. If I know that's the relation between both, so if I know U, by double integration, I get the free energies. And these differential equations I get, they're generated by basically the Gelfandicke KdV potentials. So I don't want to go, that's a long story I don't want to go into. So I'll just tell you that I can generate these sort of potentials by recursively. And here's 2 examples, R2 and R3. This is for the so-called 2,3 model or the C equals 0 multicritical theory. That's R2. And this is the 2,5 model or the C equals minus 22 to the 5th multicritical theory. That's R3. And with a specific normalization over there and over there, I can get an equation which is quite familiar. Well, this is in the conventions of Gelfandicke KdV potentials. Maybe sometimes in mathematics you use slightly different conventions. That's the polynomial equation, 2nd order nonlinear. And here's the Yangley equation, 4th order nonlinear. And then I have 6th order, 8th order, and I have an infinite tower of differential equations that I can tackle. And some of them we tackle one by one because we want to really access as much as possible about the equation. But there are other contents that we can tackle generically at arbitrary k. There is no closed form expression for these guys generically, but parts of these Gelfandicke guys we can get generically. So we can do some calculations. So what happens if we play with these guys? Here's, by the way, the string equation generically for the 2k minus 1 theory. So again, there's the Gelfandicke dude, some normalization, and Z. Z is basically the string coupling. And you can compute free energies. Here's the free energy in the 2,3 model. Here's the free energy in the 2,5 model. They're just numbers. So it's a little bit like if space-time is rigid, it's fixed. But you have to, these numbers do grow 2g factorially fast. And that's it. So this is perturbative expansions, and you can actually generate a lot of guys. I think in 2,3 we've gone to genus 1,000, something like that. What is their non-perturbative content? So for polynomial 1, it turns out that instanton action comes in pairs and is resonant. This was shown 12 years ago by Gorafalidis, Itzkapev, and Marino. And this is sort of the first instance where we saw that there was something that there were surprises. Instanton actions come in pairs, and here's the one instanton sector that you can recursively compute by just plugging into the string equation, and you get an asymptotic series as well. For the Yang-Lee, they also come, well, now these plus minus are independent, so actually I have 4 guys here. Same story. You can compute all these people. So all this doubling of instanton actions and doubling of sectors is very cleanly seen at this level because I'm just solving the differential equation of whatever order it is. So it's not really a huge surprise. How do I then write down the solution? Here's the solution just for polynomial 1, which is sort of simpler to write now. It depends on 2 trans-series parameters, sigma 1 and sigma 2. Then there's the resonant factor there. So there's just this A, n minus m. And then there's asymptotic sectors, these phi guys here. Those are the asymptotic coefficients. There might be some starting order. And there's some logs. The logs are not really relevant. They're not even an asymptotic. They go up to some maximum number. And they're basically associated to the fact that the trans-series parameters exponentiate. So they're not just multiplicative overall factors, but they also exponentiate. And the reason why they exponentiate, of course, is because these log sectors are not independent. So this is the structure of a 2-parameter trans-series solution. And generically, this is what happens. So this is the order 20, if I'm not mistaken, and these are the 41 multi-critical models. These are singularities on the Borel plane. They have these sort of funny patterns. This is the approximate lemniscate. And this would be the distribution of multi-instanton, naive multi-instanton, and Stokes lines. Of course, you could think that I can also have, beyond naive, I could also have every possible linear combination, in which case Stokes lines would be dense. In tests that we've been doing so far, this is not happening. So it seems that we have some extra guys coming up in the imaginary axis, but there's really not a dense amount of Stokes lines here. And so, but anyways, regardless of whether that happens or not, it's clear how symmetric Borel planes are. And of course, I'm giving you here 2 examples, but I could basically infinite amount of examples. And Borel planes singularities are completely symmetric, and so the phenomenon of resonance is, I think, very cleanly seen at this level of string equations. All right, so how do we explain this? So one thing that you could ask, or the first thing I will tell you about, is how to explain this in boundary conformal field theory. So if these things are string theories, I should be able to do a boundary conformal field theory calculation, and using these already pre-advertised negative tension d-branes, and reproduce all these sectors. So again, I don't want to go into the technicalities, so I'll just show you a couple of plots. We'll be doing this in minimal strings, which involve basically 3 components. There's the old minimal models of BPZ, which have that central charge labeled by P and Q. Mostly, I'll take P and Q to be 2 to K minus 1, just to that's the simplest possible example. Then there's Liouville theory. Liouville theory is sort of a boson with a background charge. B is the Liouville coupling, or if you want, B plus 1 over B is the background charge of the Liouville, which has that central charge. And then there's the usual BC ghost, the parameterization ghost of string theory. And of course, these 3 central charges have to add to 0, which gives a relation between B, P, and Q. All right, and there's a whole story behind this that I don't want to get into. What are the sources of non-perturbative effects that I could have in Liouville theory? There's 2 types of d-branes, basically. There are so-called FZZ d-branes, and you can think of here is the, previously this picture was the spectral curve of a matrix model, but it turns out, this was shown by Saber and Shi, that you can also think of this as the moduli space of the FZZ d-branes. So it's sort of, now here I'm thinking of it as the moduli space of FZZ d-branes. And so the FZZ d-branes are labeled by a parameter. I'm choosing here the uniformization variable on this curve. And it's sort of, you can think of it as a point particle d-brane that I can put anywhere here on the moduli space. Those are the FZZ d-branes. And it turns out that their amplitude. This is the disk amplitude. So in the same way that when you're doing closed strings, you have a sum over a genera. So I have a sphere, a torus, a bitorus, and so on. When you're doing open strings, the sort of Feynman diagrams are now disks, annuli, biannuli, and so on and so forth. And I have to sort of know how to add all these people together. So this is sort of the three-level contribution. That's the disk amplitude for the FZZT, which is given by an integral over the spectral curve, or the Riemann surface, which is its moduli space. So, okay, this is a huge story, so I'm trying to convey in one sentence. But that's not all the sources of non-perturbative effects that you can have, not only the FZZT branes. You can also have other types of branes, which are known as ZZ branes. ZZ branes are sort of differences of FZZTs, and you should think of them in some sense as sort of space-time instantons. They're fixed at the point in the spectral curve. So the only place where I can put whereas FZZTs, they can pretty much go anywhere, I can only put ZZs at the saddles. And since they're labeled by N and M, okay, I guess we put them differently. Anyways, they're labeled by two integers, the 1, 1, the 1, 2, and so on and so forth. So what we want to ask is, these are the natural sources of non-perturbative effects. They give rise to e to the minus 1 over gs corrections for minimal strings. What happens generically? So there's, probably one of my favorite papers in string theory is an old paper by Polchinski that tells you that the combinatorics of all these guys, of here's the disk, here's the annuli, we're not doing any higher, but anyways, the combinatorics of all these disconnected diagrams, they exponentiate. And so this is, if you just have all the possible Feynman diagrams, if you will, of the D-branes, this is the result for the one instanton partition function divided by the non-perturbative partition function divided by the perturbative partition function. This is the one instanton correction to the free energy. It's going to be of that type. And this is, we're looking at basically corrections to the partition function, which means we're looking at these space-time instantons, which means that we're looking at the ZZ branes. Because the ZZ branes are given as differences of FZTs, I can equally write that correction in this way. So here's the difference of two FZZTs in the sheet alpha and the sheet beta, and that gives me DNM. That would be that difference, and then I have to do the same with the annulus. There's more combinations, and I do an integration over the modulus, x, if you will, x as a function of theta, and basically it's going to be over, it's going to localize on the saddle points of this integration. And so this is a story that already has been known for a long time when it comes to just doing the standard ZZ brane corrections. So what happens if I do a calculation that involves standard ZZs and negative tension ZZs? So with standard ZZs, it's actually very well known, and there's huge literature on this. You just think about it, they're a difference of FZT, so you think about it as a cycle that goes through the location of the ZZ. And if you compute, that's the result here in blue, this is what you get. There's a prefactor, and then there's an exponential basically of the disk amplitude, which is the instanton action. What would happen if I, instead of doing a ZZ, I do a negative tension ZZ? Basically, it's going the other way around. Well, I get a minus sign there and a minus sign there. And then if this was the whole story, I would perfectly accept if you tell me that's lame. I mean, that's just, what's that? For the moment, one thing I can tell you is that this matches all the prefactors that you get on the boundaries of the trans series. So if I'm on the horizontal multi-ZZs or on the vertical multi-negative tension ZZs, everybody matches. So I'm not even expecting that would be like a great feat, because there's basically almost nothing to do there. So what we really want to know is what happens in the bulk of the trans series, where I have infinite more sectors that I still need to match. In order to do that, let's first talk about the 2ZZ amplitude. The 2ZZ amplitude, now I have FZZTX and FZZTX tilde. And I need to look at their differences. So I'm not doing the pictures anymore, otherwise it doesn't fit in a slide. So the A minus 1, these are the disks. Okay? I'm sorry, my phone is making some noise. The zeros, and I have 3 zeros, I'll tell you in a second what they are. They are the annuli. So this guy is the one that comes from the difference of SSATs at x, the difference of SSATs at x tilde for the annulus. And then, of course, because I have an annulus, I can have an SSAT x and an SSAT x tilde, and I need to consider those differences as well. This guy has a logarithmic term that we're taking already out. That's why there's a hat there. And the logarithmic term, it's a logarithm of x minus x tilde, if you want, with the exponential just becomes a sort of a monomial contribution over there. This looks like a van der Monde. In fact, it's not a big surprise that this boundary conformal field theory is in some sense dual to the matrix integral because it's giving exactly the same results. And you can do this computation and you get well-known results. So the question is, what happens if instead of having two ZZs, I now have a ZZ and a negative tension ZZ? And this would be a contribution to the 1-1 sector. So this would be the first guy in the bulk of the train series, which is highly non-trivial. Well, now the same thing kind of happens. I have my disks for each guy. I have my annuli for each guy. And I have my mixed annuli. But because there's an extra minus sign there, what before was a monomial now is a pole. So the minus sign that comes from this regularized annulus results in a double pole. So this is no longer a story about, oh, there's an extra minus sign. This is a story about non-trivial integrations that I have to do, which include residue contributions. So I'm not only going to do a saddle point calculation. On top of the saddle point calculation, I have to include a residue term. And that's basically going to change the whole calculation, and it's going to give a lot of non-trivial stuff. And by the way, we could do any sectors you will. So I'm not even, this is not the slide to be explained. It's just a slide to give an idea that there's basically no limit to the calculations we can do as long as we stay within annuli. Bi-annuli is something a little bit harder. And also, another point I would like to make is that every time we regularize this sort of annuli that is jumping between different FZZTs, we get extra factors, extra logarithms that basically materialize themselves as van der Monde-like determinants that are appearing here as prefactors. And so all these terms have a very much matrix model flavor. All right, so final or third point of view on the exact same calculation. Can I also do this from the point of view of matrix integrals? So what we would like to do, and this is exactly the same story as in boundary conformal field theory, so I could have said this earlier, but just not to repeat myself, we have a train series that comes from the string equation, and here I'm just writing it for the partition function. It just doesn't matter. And it's something that looks like that. We've already seen in the case of polynomial 1, for example. How can I identify all these sectors from a matrix integral calculation? So here I have my matrix integral. I'm integrating over matrices M, which are of size n by n. And I just go to diagonal gauge, where I focus on the eigenvalues of the matrix, integrate out the off-diagonal people that kill the volume of the gauge group that just leave me 1 over n factorial. I have my van der Monde over there, and I have my eigenvalues, which I need to know where to integrate. So I need to specify integration contours for these guys. So if I'm asking which train series sectors match which matrix integrals, in some sense I'm asking which train series sectors match which sorts of choices of contours, saddle point integration contours, from the point of view of the matrix model. The identification is done by looking at Stokes discontinuities. So the train series yields Stokes discontinuities that look like this. This is the discontinuity of the perturbative guy along the forward direction. I'm assuming that A is real. So there's, let's say, the multi-instanton sectors, and then there's Stokes data. Sometimes we call these guys Borel residues because this is not, these are not the Stokes vectors that appear in the bridge equations of alien calculus. Well, they're related, of course. These are the coefficients that appear in front of the logarithm branch cuts on the Borel plane. So it's basically, again, Stokes data, but slightly friendly, more user-friendly name. These discontinuities may also be computed from matrix integrals. So they're associated to ratios of this type. And I have to compute integrals of this type. So I have to compute k-dimensional integrals over correlators of matrix model determinant insertions. And so if we do this calculation at the matrix integral level, we can match against train series. They will match. They give the same result. So let me show you how does that go. So the first thing is the story of the anti-eigenvalues, right? So at the level of boundary conformal field theory, the negative tension difference was just an overall minus sign in front of the disk amplitude that then produced a lot of novelties. In the matrix model side, it's about an involution. The involution between the physical sheet of the spectral curve, which was the one that was plotted in blue earlier, and the non-physical sheet of the spectral curve, which was the one that was plotted in orange earlier. And basically, it's just an inversion if I want to jump from one sheet to the other, which has this very simple effect at the level of the x and y coordinates on the spectral curve. At the level of determinant correlators, there's another thing which is happening, which is the following. So if I, quote unquote, try to tunnel an eigenvalue into the involuted non-physical sheet, which would be just removing an eigenvalue from the cut and taking it in the orange side of the spectral curve, it turns out you can show that there's an equality that this correlator matches this one that I have below here. So the sign, the minus becomes a plus, and the determinant gets inverted. And this is literally thinking of these involuted eigenvalues on the orange sheet as holes on the physical sheet, and hence the name anti-eigenvalues. In fact, if you look at the electrostatic, you can think of these eigenvalues as a two-dimensional gas, Coulomb gas of particles, and if you look at the electrostatic interaction, they really switch signs. So they're really anti-eigenvalues from the point of view of the two-dimensional Coulomb gas. And so we call them anti-eigenvalues. So in order to do calculations at the level of the matrix model, here's the two simplest things you can do. You can tunnel a single eigenvalue, and so you have to basically evaluate this integral over some specific contour. I'll draw the contour in a second, of a determinant correlation. And if you tunnel a single anti-eigenvalue, you have to compute this other integral. Slightly, already it's giving you the flavor that there might be some poles, and there's a plus sign over there, and you also have to tell you what exactly is that contour. And you can match the resurgent relations with these contour deformations of eigenvalues and anti-eigenvalues, also to get the discontinuity along pi. So there's basically, because I have a plus a and the minus a, I have a discontinuity along 0, and I have a discontinuity along pi. And everybody matches. And this is the analog calculation in BCFT, which would have been this one, with sort of the Vandermonde of 2 ZZ branes, and this one, which is sort of the inverse Vandermonde, where I have one ZZ and one negative tension ZZ. So here's a picture of what's going on. So I have basically a Stokes discontinuity along the positive direction, and I have a Stokes discontinuity along the negative direction. This is the potential, say an example in blue, an example of the potential of my matrix model. I had n eigenvalues on the cut. I remove one eigenvalue. I put it at the pinch, and I can describe what's going on the forward Stokes automorphism. But I could have done the opposite. I could arrive here at my cut. I create a pair, eigenvalue, anti-eigenvalue. Hence, the number of eigenvalues grows by 1. And I grab the anti-eigenvalue that came from the pair, and I put it at the inverted pinch. And that gives me that sort of, the anti-eigenvalue tunneling, and it describes to me exactly the backward Stokes automorphisms. And now that I have a description of forward and backward, I can access the whole trans series. In fact, here's another picture where I'm at any sector I will. This is the spectral curve. I can either do eigenvalue tunneling, which is that picture. I can do anti-eigenvalue tunneling, which is that picture. And the thing that's going on here is that the matrix integral is already computing immediately the whole resonant kernel in the discontinuity. So I'm not identifying sector by sector, but I'm identifying resonant kernels with matrix integrals. And here's a slightly more clean example of what's going on with the integration contours. So this is the same example that I talked about in boundary conforming field theory earlier. There's the pole, and now here's what I would call the contour before and after the Stokes transition for eigenvalues in blue. And here's the contour for anti-eigenvalues already going through the non-perturbative saddle. So there's the bar for the eigenvalues. And when I compute the difference, so that would be the Stokes discontinuity, I no longer would have what would be sort of familiar from earlier, which is I have a non-perturbative contour for eigenvalues and the non-perturbative contour for anti-eigenvalues, but there's also a residue contribution. And that residue contribution is really allowing you to see exactly the results that you would get from string equations or from boundary conformal field theory. So here's the message. Everybody matches. You can do the calculation in three completely different ways. You get exactly the same result. And you really compute the whole structure of train series. So this plot that was sort of motivational earlier materializes. Here's results. So you pick string equations, boundary conformal field theory, matrix integrals, whatever you want. We compute ZZL instant on amplitude. This has been computed. I mean, the literature is probably, I'm for sure forgetting someone, which I immediately apologize. And this has been computed by a lot of people. That's the result you get. Negative tension ZZ instant on amplitude. This is what looks like the lame result, because, it just got a minus sign there and minus sign there and nothing else. Well, it still yields the analytic canonical Stokes coefficient because they satisfy some backward-forward symmetry. So Stokes data has factors of I that appear. And you could say, OK. But if you decide to go slightly harder, here's the 1-1 sector. So there's this guy, and then this is an asymptotic series, so that comes at order 1 over GS. Then there's something that comes at order GS, and then there's stuff at order GS cubed. And really, I mean, this is a non-trivial result. And you can compute this with matrix integrals, with boundary conformal field theory, with string equations. You always get exactly the same result. So everything is really matching now non-trivially, right? It's no longer a lame minus sign. It's really poles that lead to much more complicated integrals and much more complicated results. And here's the 2,1, well, the non-trivial part of the 2,1 sector. I'm sort of removing some sort of simple part, and it gives logs and Euler-Mascaronis. So you can see that we're really starting to reach the non-trivial log sectors of the train series. These are the log terms, guys. And we're already computing really non-trivial Stokes vectors. In particular, there's some universality here. It seems that all these models, non-trivial Stokes data will include Euler-Mascaroni terms. So this is quite, quite curious. So in fact, let me just end the calculation by making a remark on Stokes data. I'll specify for Ponlevé, which is probably something this audience might rather. So Stokes data are vectors that organize. These are really the Stokes guys that appear at the level of Eccles bridge equations. They organize basically occupying the third quadrant of the plane. And their vectorial structure is very simple. This is basically integers. And what's not simple is that they have some quote-unquote a norm in front of them. And so that's the numbers that we would like to obtain. So we've obtained a generating function for all these numbers. It's basically dictated by n11, and then there's a 1 over gamma function. And we can get a lot of non-trivial Stokes data. So the one that was known by François David a long time ago, and all the other things that start having Euler-Mascaronis everywhere, and squares, and so on and so forth. All these things that were, by the way, uncomputable directly from string equations. You could only access them numerically by looking at asymptotics. Now you can directly compute them from either a random matrix integral or from a boundary conformal field theory calculation. And you can get an analytic number. Of course, if you want to go one by one, good luck. That's going to take some time because the calculations are hard. So you probably need to play some resurgence games to try to find generating functions one by one. But at least some of the lower examples, you can just do the calculation, do your very honest integral, and you get these numbers out. And then you can check. Okay, maybe this is getting a little bit too technical, but you can check that monodromy closes. So remember that we're looking at Ponlevé equations, which only have double poles. And so you could check the monodromy, and it closes. So let me just say monodromy orbits close and not dwell too much on this slide. What I rather just point out is that the fact that Stokes data is transcendental boils down to quite some simple facts from the 2 points of view. From the point of view of resurgence, I have a 1 over gamma function, which is appearing here in the generating function of Stokes data. And that 1 over gamma is basically generating a lot of zeta numbers and Euler-Mascaroni. Well, you can think of Euler-Mascaroni as some sort of regularized zeta number as well. And from either boundary conformal field theory or matrix integral calculations, this is associated with the fact that I'm doing a lot of log x integrals. And log x integrals also generate a lot of transcendental Stokes there. All right, so I think I have 5 minutes left, maybe less, I'm not sure. So let me just point some things that we could think about going forward. So the first thing I'd like to do going forward is go back to Tatooine, because it's much warmer than here. And I will hopefully go by the end of this week. But before that, let me just end by saying a couple of other things that we could do. So other backgrounds that we could look at, JT gravity. So there's been a lot of recent interest in JT gravity, Joukiffe tidal wave gravity, because it relates to SYK models in condensed matter. It relates to actually black holes in 4 dimensions. So maybe something can be said there. Now, it turns out that it's described by a double-scaled matrix model, which has a very simple spectral curve. And so we can apply this machinery here. And here we have the standard multi-instanton and multi-negative tension, ZZs, if you will, corrections. And here's the 1-1 and the non-trivial part of the 2-1. They are quite, friendly formulae compared to the ones I showed you earlier. So we can really access the full structure of non-perturbative JT gravity. Even though there is no string equation, by the way, but we don't need it. We can either resort to boundary conformity theory or to matrix integrals. And so one question going forward is, what could be the relevance of this whole non-perturbative construction towards black hole physics? I do not know, but maybe that's something that one could think about. Here's just to convince you that everything is good with JT gravity. Here's the Borel plane. You can see the singularities. This is the perturbative expansion. They're really symmetric. And here is just, we improve it with a conformal transformation so you can also see the multi-instanton guy. So that's one thing to think about going forward. Another thing to think about going forward is topological strings. So if we recall the remodeling conjecture of Bouchard, Clem, Marino, and Pasquetti, we can actually apply matrix model formulae to topological strings with a simple, let's say, quote-unquote correction to the Bergman kernel in the topological recursion. So, I mean, we don't need to go into all those technicalities, just to mention that we're sort of restricted. So our examples are one-cut matrix models with arbitrary number of pinches, but there's really just one cut. So from the point of view of topological strings, we're restricted to looking at the local curve, which is this toric Calabi-Yau, which is just basically a fibration over a sphere with 2 line bundles. If you don't know what that means, it doesn't matter. It's just a specific background which has this horrible-looking spectral curve. It's classified by an integer p, and the p appears there. And even though the spectral curve is quite horrible-looking, this is quite computable. This is the non-trivial part of the 2,1. And it gives that result. And you see, oh, look, there's an Euler Mascheroni. Oh, there's a log. I'm not showing any other components of these, I mean, we have computed them, but for example, the 1-1 sector, it basically occupies 2 slides. So, I mean, there's no point in showing it. And you could say, OK, fine, that's yet another system. Yes, that's yet another background, but it's one which is quite peculiar, or interesting, let me say it. But recently, Garofalidis, and Marino have been thinking in Chern-Simons and in topological strings whether Stokes data can be used as topological invariants. So, here is a system that now we have a lot of control over. So we could ask if the Stokes data of the local curve can be classified and it can be used as topological invariants. So here's a first interesting calculation. In standard toric Calabi-Yaus, they have a special point in moduli space, which is known as the conifold point. And the local curves don't have the conifold point. They have another critical point, which double scales to c equals 0, to Ponleville 1. So that's quite interesting. And all those formulae that you can get from different sectors of the local curve, here's for the third local curve, they literally double scale to Ponleville 1, and this can be literally checked even for that expression that was occupying 2 slides that I mentioned earlier. So this raises the question, whether can we understand Ponleville-Stokes data geometrically? Is it some sort of, so maybe we have some sort of topological invariance of the local curve dictated by the Stokes data of the local curve, and it has to double scale to the Stokes data of Ponleville 1. So maybe there's also a geometrical understanding of Ponleville 1 Stokes data to be unveiled. And yet another example, which we still haven't managed to finish, but let me just mention, because maybe somebody can have some interesting feedback, is to try to do critical string theory now on an ADS background. So most of the ADS backgrounds are really hard, but there's one ADS background which is sort of achievable, which would be ADS3 cross S3 cross T20. So we're just looking at the bosonic string. because this is a WCW, which is, has been quite studied. And even here, you could say that looks pretty nasty. But there's a correspondence between H3 is just basically the Euclidean version of ADS3. There's a correspondence between correlators that you can compute in ADS3 and Liouville. And that's the correlators that we've just computed earlier with both ZZs and negative tension ZZs and so on and so forth. So we could map the hard ADS calculation to our earlier Liouville calculation. So there's a divergence that appears for these ADS2 branes, which are sort of the analog of the FZZTs, that we still have not managed to regularize. This is not a very problematic divergence. The same happens in Liouville, by the way, but there we have sort of input that comes from the matrix model that allows us to regularize it better. So this is still something to wrap up. And just my personal final questions is whether we can classify Stokes data for all multi-critical minimal strings. Probably yes. I mean, we're looking at this, and so far we cannot say it's impossible. We'd like to have closed form expressions for the full non-perturbative partition functions, because now we really have all these sectors that we need to tackle at once. I'd still like to know, this is how I started, talking about these corrections. Where are they hiding? This is still something to see. And then maybe one day, certainly not in the near future, but maybe we can say something about ADS, CFT, and more generic large N dualities. Thank you very much.
Thank you. Maybe it's too naive, but when you speak of negative tension, this makes me think that the theory is unstable.
Yes, so in some sense, what we're discussing here is the kinematics, it's not the dynamics. So what we're saying is that from a kinematical point of view, you need all these sectors. Then you can ask what happens dynamically. So one thing, that's why I was saying that it would be interesting to look at these non-perturbative partition functions. Because then you can start thinking of what are the different phases that the theory can be on, and what would be the physics in all those different phases. For example, an analog would be the Boutreau classification of singularities for Ponleve 1. So you have the Tronqués, the three Tronqués, the generic solutions. These are different phases of, if you will, 2D quantum gravity. So, but that's sort of the next question.
Andy?
So on one of your last slides, I think maybe slide 56.
56.
Yeah,
sorry,
right. Yeah. So there at the bottom, there's some, what I guess is some observable in the topological string.
Yes.
That involves this gamma E. And what observable is it?
So the observables we're focusing on is the partition function.
It's, right.
So we're ratios of partition functions, which are corrections to the topological string free energy.
Right. So Z00, I guess I kind of understand. What are the other ones? So what's like Z10?
So this guy would be the perturbative partition function. This guy would be the guy with 2 toric d-branes and 1 negative tension toric d-brane. And I'm sort of removing the easy part. So, another way, there's nothing to cover. Let me just try to cover this guy. Forget about this guy. And so what I'm really computing is the amplitude for the free energy that has 2 toric branes and with standard toric branes and 1 negative toric brane, if you will. That's the correction to the free energy we're computing.
I see. And so there's some systematic rule in the topological string for computing. So with the regular branes, I know, but with the you're saying with these minus branes, there's also some systematics. Okay.
Yes. So which follows directly using basically the remodeling conjecture. So you go back to the matrix model, you see, you can even forget about branes. You just think about eigenvalue and anti-eigenvalue tunneling, and you directly apply the matrix model formula to the spectral curve of the topological string.
Good. Thanks.
You mentioned that all these numbers are transcendental, but I guess you rely on the conjecture that stuff like gamma E is a transcendental number, right?
Sorry?
So you rely on the conjecture that gamma E is a transcendental number.
Okay, fine.
But so to phrase the question then, so is there, or do you think there's a possibility, because all these kind of numbers arise as asymptotic expansions in these string theories, to somehow generate something that is pure inside, say, gamma E, to actually get a handle like on questions like the irrationality of these numbers? from the perturbative expansions. So somehow remove the contamination, say, by log of 2, like in this example there.
Yes.
Because the log of 2 is, of course, known to be transcendental. So any irrationality proof is spoiled by the gamma of 2. So can you somehow generate something that is sort of pure in gamma?
Well, the short answer is I have no idea. But one thing I can tell you is that I'm expecting that on all these problems, all Stokes data will be generated by stuff of this form.
Right.
So more complicated, maybe products of these guys, but at the end of the day, the core object is going to be 1 over gamma function. So you're not going to learn anything else about number theory except what you know from 1 over gamma. Sorry.
Right. Thanks.
I have a question about the JT gravity part.
Yes.
So can you explain actually what exactly you did there? Because you just had time to flesh it out. But you had like some hope for black hole lessons. Like, do you have some ideas there? Like, what
So I'm sorry, I misunderstood.
Oh, sorry. I mean, like, what do you mean by relevance for black hole physics? So do you have something exactly in mind when it comes to these results?
This is just asking what can we do with these things. So I mean, when you write down say the spectral curve for JT gravity and you try to compute the free energy, whatever, you know that it's describing for you the near horizon geometry of 4-dimensional black holes. And so you could ask, well, now I have a perturbative description of that near horizon geometry. Maybe I can get some physics out. And of course, there's lots of stuff done by Sachenko and Stanford, and then following up on that. And you could ask, what are these non-perturbative corrections giving information about? I have no idea. So certainly, they will not be just the standard things. And in fact, if you go back to the Sachenko-Stanford paper, you already had that first guy, the 1 instanton guy there. And that was already discussed there. So you could ask, what happens if I now include everybody else? Maybe I'm going to access some regime which is more unphysical of the black hole, or maybe I'm going to access some regime where I can learn more things about, I don't know, evaporation or whatever it is. This I really have no idea, so I mean, I cannot say anything but to bubble.
So you would like to think about them possibly as some additional saddle points?
Some additional?
Saddle points?
Yes, definitely. I mean, you have all these other extra things which are associated to the fact that you have this trans series, which is, if you want, two-dimensional.
But you don't have necessarily geometric interpretation for them or anything
That's
like
why I have 3 question marks. Sorry.
Well, thanks.
So this is more to, I mean, if anybody has some comments, I would prefer to hear that rather than I have anything to say.
I have another question. There's a big room.
Thanks. I'm sorry if this is a rather naive question, because it's rather a long way from anything I know anything about.
No.
I'm struggling to understand the exponentially large corrections. You describe them as corrections.
Yes.
So am I right in thinking they're exponentially large solutions to your differential equations, essentially linearized about the perturbative solution?
Yes.
So how am I to interpret that, since they're much bigger than the thing
Well,
you're
let me see if I can
about?
go back to that slide. At some stage I showed it. Wait. Here we go. So here we have, this is the solution to Polynomial 1.
Mm-hmm.
And it depends on, it's a second order differential equation, so it depends on, if you want, 2 boundary points, 2 boundary data, sigma 1 and sigma 2, or 2 initial data, whatever you want. And then there's going to be exponential suppressed and exponential enhanced people. And you can always say, you can always specify initial data. And you can specify initial data where you don't see the large growing guys, at least not in the first, I don't know how to call a slice of a pentagon, on the first slice of the pentagon. And then there's no exponential guy. You can start, either with just the perturbative or the perturbative and the exponential suppressed. These are the classical solutions of Boutreau, right? The tritronqué and the tronqué. And then as you start going into the region where there are poles, you need to start turning on these guys. And then they would be appearing there. If you ask what happens if I turn on both exponentially suppressed and exponentially enhanced people already on the first slice of the pentagon, then this means that you're in the general solutions of Boutreau. They already have poles everywhere. So in some sense, the perturbative solution you started off with is washed away into the fact that everything is populated with poles.
Okay. Thank you.
Last one.
So I should have asked this in September. Why do the ODEs in this context, why are they always integrable? What's the
Why,
intuition?
sorry?
Why are they always integrable?
Why are they all integrable?
Yeah, what's the intuition?
Because they all come, so it's basically, if you will, it's because there's a matrix model underlying these all structures. So they're all associated to these classes. So first of all, only in very special models you have all these ODEs, right? So these the multi-critical strings and minimal strings. So when you start going to topological strings or full string theory, those ODEs are all gone. The reason why in those simpler models you have ODEs is because there's a matrix model underlying the structure. And so the matrix model basically has hidden in itself these ODEs. But I can explain to you the technicality in more detail.
Yeah, I could take that question further backwards now.
Okay.
But
Okay, let's thank Ricardo again.
Thanks very much.
So we have a break now for half an hour for coffee. An important announcement though, there's a lot of travel disruption predicted this week, and it may affect many people when leaving on different days. The plan is to have a sheet of paper out here somewhere on one of the tables. If you're leaving particularly on, say, Thursday, Friday, Saturday, please just going to Gatwick or Heathrow or Stansted or to King's Cross, St. Pancras, just put your name down with a time of when you need to be there, and we're going to try and arrange to make sure everybody gets there one way or another, be it by bus or shared taxi or whatever, okay? So it should be out there now, but at least by lunchtime there'll be a sheet. And we want to try and get this information today if possible, so we can try and avoid some of the predicted disruptions, okay?